And welcome to the Qiskit Quantum Seminar. I'm Katie McCormick. I'll be your host today, and I'm tuning in from Fair Oaks, California. As always, we'd like to hear from you all. Where are you tuning in from? Drop a line in the chat and let us know. And while I wait for your responses to come in, let me welcome you all again to the 176th Qiskit Quantum Seminar. The seminar takes place every Friday at noon Eastern Time and will be hosted on the Qiskit YouTube channel. You can always subscribe to go back and catch up on anything you missed, but you can only ask questions here live now during the seminar. Today, we'll be hearing a talk by Daniel Slichter about quantum nanomechanics with trapped ion motion. Hi, Daniel. How are you doing?
I'm doing well, thanks, Katie. How are you?
Doing good. And where are you tuning in from?
I'm tuning in from Boulder, Colorado, where we're here on the NIST campus.
Awesome. Well, welcome. And I see in the chat we have somebody from Portland, and I'm sure there will be more coming in soon. So I'll start with an introduction of Daniel, and then we can get started with the talk. So Daniel Slichter is a physicist in the ion storage group at NIST in Boulder, Colorado. His research focuses on quantum information experiments with trapped atomic ions, with an emphasis on developing new paradigms for scalable trapped ion quantum computing and creating long-distance quantum networks with trapped ion memory and computation nodes. He received his bachelor's in physics in 2004 from Harvard University and his master's 2007 and PhD 2011 in physics from the University of California, Berkeley. His PhD research was in the field of superconducting quantum information, where he demonstrated the first continuous high-fidelity measurement of a superconducting qubit and studied quantum feedback, measurement backaction, and near-quantum limited parametric amplification. Whenever you're ready, Daniel.
All right, great. Thanks, Katie. All right, let me get my slides going here and share my screen. All right, and laser pointer, how does this look? Great. Well, thanks, Katie, for the nice introduction, and thanks for having me on the Qiskit seminar. It's great to be here, and I'm excited to tell you about some work today that our group has been doing. This is not directly down the sort of quantum computing alley, and I've done sort of quantum computing work both with superconducting qubits and parametric amplifiers, as well as trapped ions in my career. But this is sort of another fun thing that we work on in our group, which is thinking about the motion of trapped ions as nanomechanical oscillators. And so this is a little off the qubit focused track, but I hope it will be interesting and enjoyable. I think we have some nice results to share. Okay, so I'll go ahead and get started here. I'm going to first just give a little bit of a background on the NIST ion storage group, because I know this is oftentimes a more superconducting heavy focus or theory heavy focus. I'm going to talk about trapped ions, which are a quantum hardware platform. And what our group does is we work with individually resolved ions that you can trap in ultra high vacuum, and then you can manipulate them and you can measure them with lasers and electromagnetic fields. So this is a group that was started by Dave Wineland here in the late 70s, and Dave won the 2012 Nobel Prize for some of the work that he and the group carried out over the years. We work with traps where we hold ions both in sort of small strings like this, using RF electric fields to trap them, as well as in these sort of 2D self-organizing Coulomb crystals in a magnetic field in a Penning trap. And we've got a lot of different topics that we work on in quantum information, in quantum metrology, in quantum simulation. So I don't have time to touch on all these sorts of things today, but not only do we do sort of quantum computing and quantum networking work, but we also have really incredible optical clocks, ultra precise molecular ion spectroscopy and things like that, work on simulating quantum mini body physics and bosonic systems, all sorts of things. For this talk, I'm going to focus on these sort of topics here around quantum fundamentals, around ion motion as sort of a quantum degree of freedom of interest, and then how we can use this for quantum enhanced sensing and to probe surface science topics. So here's just to give you a sense, you can see my face, I'm in an office, but literally outside my window, these are the mountains that we have here, the Flatirons, and here's a recent picture of the group. There's a link to the group website in this QR code, and if people are interested in learning more, we have positions open. You can shoot me an email or look on the website. All right, so I'll get started now with the content of the talk. So I'm going to start out just giving a little intro to trapped ion motion and how that works. I'm going to talk a little bit then about how we do electric field sensing with ion motion. And then I'm going to talk about quantum squeezing of motion and how you can use that for quantum enhanced sensing. Then I'm going to talk about coupling of motional modes and protected modes, and I'll explain what those are. And then finally, I'm going to talk about some coupling of motion in different wells. So we'll get started off with the intro. So trapped ions as sort of a quantum hardware platform. Most commonly, you'll sort of think about them as qubits, where you'll say, all right, there are two internal energy levels associated with the electron spin and angular momentum, the nuclear spin of a single, atomic ion that's trapped by itself in ultra high vacuum away from everything else. But actually, the motion of a trapped and laser-cooled atomic ion is another quantum degree of freedom that is important. It's important not just for sort of quantum computing, but it can be used as a nanomechanical oscillator, as we will see today. So why is this sort of an interesting and compelling quantum platform? Well, the ions that we trap are all identical. They've got the same mass, the same energy structure, everything like that. You can hold on to them for hours or days or weeks. So that's not as long as a qubit that's fabricated on something, but it's longer than a neutral atom in a trap, for example. The coherence times can be really long. I mean, even the better part of an hour, which is really pretty outstanding. And you can also do very high fidelity control of the spin state as well as the motion, and sort of the kind of gate errors that people achieve. Currently, the record for single qubit gates is about 10 to the minus 7 error per gate, and the 2 qubit gate is now considerably below 10 to the minus 3 error per gate. You can also read out the state with very low error. And if you have multiple ions together and you're trying to do quantum processing with them, you can actually reconfigure which qubit talks to which qubit by moving ions around or by changing your laser configurations, which is a nice feature. But I'm today going to focus on the fact that this motion of the ion is a quantum nanomechanical oscillator. It's single atom or few atom nanomechanical oscillator. And basically what this means is that these ions that we have, this is a wonderful quantum playground. We've got this coherent, tunable system. Things can be coupled together with both spins and these quantum harmonic oscillators. So let's launch in a bit. So how do we hold on to these ions? The traps that we're going to talk about today are all what we call RF ion traps. The way this works is as follows. So the canonical sort of linear RF trap looks like this. You'll have 4 rods. The 2 rods in red here have a radio frequency voltage applied to them. And the rods in gray have a static voltage applied to them. You say, okay, why are we putting radio frequency voltages on? Why don't we just use static electric fields? These ions are charged to hold them in place. And the reason is that if you go back to your favorite E&M class or textbook, you can't actually make a minimum in space using just static electric fields. So you can't make a trap using just static electric fields. But you can make a trap if you make oscillating electric fields. And the way that works is this. If you look end on this trap here, you can see the electric field lines make this kind of a shape here where they avoid the middle, and this is a saddle point. It's not a minimum or a maximum, but a saddle point. So it's confining in one direction, but anti-confining in the other direction. And if we have that saddle oscillate at this radio frequency, what happens is an ion that's sort of sitting here, it might start to roll down the saddle, but as it starts to roll down, before it can go very far, the saddle becomes now confining instead of a place that it can roll down. And so effectively, if you flap this saddle up and down fast enough, there's sort of a time average potential that the ion sees that will keep it in place. So then we use that, and then we can use a static field in the third dimension here to adjust the confinement along this axis, and that lets us hold ions in this trap like this. Now, oftentimes what we'll do, instead of having these sorts of rods, which typically are something you might sort of make precision machining or laser cut things, stuff like that, you can actually unfold them onto the plane. And if you unfold them onto the plane, you get somewhat lower symmetry in your fields, but you still have this saddle point of the RF electric field. And that allows you to still have this confinement, but now in a trap geometry where all the electrodes can exist on a plane. And this makes it possible to microfabricate, like using the same techniques you would use to make a computer chip or a superconducting quantum circuit or something like that. You can fabricate complex electrode structures to hold ions trapped in vacuum above them. All right, so what does the motion look like if you have an ion in this trap? So I'm gonna show here these dotted lines represent sort of motion equipotential contours. And let's say you've got an ion trapped in here, this green thing. It's gonna have 3 eigenmodes of motion. And there are going to be motion along the directions that are the sort of the principal axes of this ellipsoid. So we'll call them X and Y, and then Z is out of the page right here. So with the typical confinement that we get, the motion here will have a resonant frequency of a few megahertz. That sort of tells you about how much confinement there is and what the mass and charge of the ion are. And then there will be frequencies. If we look at them in frequency, this X you can see is a little more weakly confining along this X than in Y or Z. So that means the frequency in the X direction is lower than, say, the Y or the Z frequency would be. Now you can also do something like add another ion, and if you have 2 ions in this well, they will actually repel each other. They're both electrically charged, so they will sit a few microns away from each other in this well. And that means that they're so close that if this one moves, the other one feels that motion of its charge quite strongly. So now we have to think about not just independent motion of these ions, but really the eigenmodes here are multi-ion eigenmodes. And if you have n ions in a potential well, there are 3 n modes along the 3 directions, n along each direction. So if we just take this case of 2 here, we can look at modes that are along this X direction, which we'll call axial modes. And you might have basically this sort of in-phase mode where the 2 ions are moving together, and an out-of-phase mode where the 2 ions are moving in opposite directions from each other. And then in the radial directions, in this direction, Y or Z out of the plane, again, you'll have in-phase modes where the ions move together, and out-of-phase modes where the ions move in opposite directions. And the frequencies for those, they will have, all of these modes will have different frequencies. So the in-phase modes here have the same frequencies as these single ion modes, but the out-of-phase modes will have their own separate frequencies. So you can actually resolve this motion in frequency space. In quantum computing applications, the fact that this motion is sort of shared between ions makes it really useful as a quantum bus to basically allow you to couple the spins of the ions together via the motion. I'm not going to talk about that today, but that's sort of a key feature for trapped ion quantum computing. But really, the point for today is we've got all these motional modes. Every single one of these modes of different modes of motion, whether it's 1 ion, multiple ions, is a separate quantum harmonic oscillator. And so that's a quantum degree of freedom that we can play with. So now I said these frequencies are sort of a few megahertz. So at room temperature, that means that KT is much larger than h bar omega. So we're not in a quantum regime. So how do we get to the quantum regime? And the way we do that is with laser cooling. And I'm going to give a little description here of Doppler laser cooling, which was first demonstrated in 1978 in the ion storage group by Dave Wineland and Bob Drollinger and Fred Walls in this paper, which is fantastic. I encourage you to read it because it's beautifully written. This was actually the first time that anybody ever laser cooled atoms. And so this is something that lots of people in AMO physics and quantum physics take for granted now, but this is where it started, is with trapped ions. So I'm going to try to explain, because people usually think of lasers as, they're hot. How can you use a laser to cool something down? And in this case, an atom. So the idea is, let's say you've got this confining potential, and you've got an atom in this confining potential, and it's hot, it's moving. So it's moving back and forth in this direction right here, right? And it might be equilibrated to room temperature, for example. And then what we'll do is we're going to shine a laser along this direction, and we're going to have that laser be close to a resonance in the atom, so the atom will absorb the laser light, and then it will re-emit, it will fluoresce and send out photons in all directions like this. So if we look at it in frequency space, if you want to do Doppler cooling, we set up something like this. So in blue, I'm drawing the line shape of this atomic transition. And then here in red, this is where we put the laser frequency. So we put the laser frequency a little bit lower in frequency than the center of the atomic resonance. Now, why do we do that? So we've got this atom, it's moving back and forth. And the reason it's moving back and forth is because it's trapped. And so when it gets too far to one side, it changes and turns around, goes the other direction. If this atom happens to be moving towards the laser beam, so the laser beam's coming right to left, if the atom is moving towards the laser beam, in the atom's frame of reference, that laser light is going to appear blue shifted, and it will be blue shifted such it's actually kind of closer to resonance here. So it's more likely for the atom to absorb a photon, and when it absorbs a photon, that basically means the photon kicks it. The photon kicks it with its momentum, and that momentum will be in the direction opposite the ion motion. So it sort of reduces the ion motion a little bit. Now, if the ion is moving away from the laser beam, the laser will be redshifted instead. And it's redshifted, so it's actually sort of out of this resonance. So you won't absorb photons. So you won't get any kicks if you're moving away from the ion. So the net effect here is that you get repeated kicks every absorption and emission cycle that sort of oppose the motion towards the laser. But then when you emit in all directions, you kind of get kicked in all directions. And this gives you overall a net slowing force on the ion. And as pointed out here, you can actually, depending how cold you can get depends on the line width of this atomic transition. But for typical ions that we have, you can get to about 1 millikelvin or so, or a few millikelvin. With the Doppler cooling here. And so this is cold enough to get you into the regime where you can actually see that the motion is quantized. You can get to this quantum harmonic oscillator regime. So the platform that we have is we've got this sort of spin degree of freedom, and I'm just going to very hand-wavingly say we've got 2 spin states and they're separated by sort of a gigahertz. I'll talk about this a little more specifically in a bit. And then tensored in with that spin is this motion, and the motion we've laser cooled, so it's in this sort of quantum regime. So we treat it as a harmonic oscillator with these different levels here, energy levels 0, 1, 2, etc. So quantum harmonic oscillator, this is exactly the same physics as a superconducting cavity, superconducting resonator would be, except here the splitting is sort of at these megahertz frequencies instead of gigahertz frequencies that you would typically see. So once we have this, we can do several different types of transitions that we can drive using our control fields. One is we can flip the spin of our ion without changing the motional state, and we call that a carrier transition. We can also flip the spin while adding or subtracting a quantum of motion. And doing this requires a gradient of a field. We'll talk a little bit about this. And we call this a red and a blue sideband. Now, I know that there's some people on the call who may prefer to speak Hamiltonian, in which case a red sideband is sort of sigma minus a dagger plus Hermitian conjugate, where this is the spin and that's the motional operator. The blue sideband, so people will recognize this as sort of a Jaynes-Cummings type interaction. The blue sideband we can drive is actually an anti-Jaynes-Cummings type interaction. So this is something you can't usually get in a cavity QED, circuit QED type of a context, but we can do this in ions, which is a nice feature. So if we can drive these sidebands, what can we do with that? Well, one thing we can do is we can actually use the sidebands to cool down to the ground state of motion. And sort of just a hand-waving way to describe that is, let's say we were in this spin down with n equals 1 quanta. We drive this red sideband. Now we're in spin up with n equals 0 quanta. And then if we excite to an auxiliary state up here that then decays, spontaneously emitting a photon back down, that process generally doesn't change the motion, but will bring us back to our initial spin state. And we've sort of cycled through and subtracted a quantum of motion as we cycled through. As I mentioned, we've got these sidebands that lets us have tunable James-Cummings or anti-James-Cummings types interactions. So if you want to do quantum simulations or things like that, this is really helpful. If you turn both of these sidebands on together, you can get a spin-dependent force, a state-dependent force, which we use for entangling gates and quantum computing. And then I also want to point out that the sidebands allow you to check if you're in the motional ground state. And basically the way they do this is with a conditional spin flip. So let's say you're in this state here in the motional ground state, and you try to drive a blue sideband, you can do that. But if you try to drive a red sideband, there's actually no level for that to go to, and so you will not drive the red sideband. So if you start here and try to drive a red sideband, if you're able to drive it or not tells you whether or not you were in the ground state of motion. And the same thing is true if you start in this up state and drive a blue versus a red sideband. So we have this really nice way of checking if we're in actually the pure ground state of motion or if we have any motional excitation at all. Very sensitive to a single motional excitation. So how would you couple spin and motion if we're doing this? Well, one way to do this is you can put on some kind of a spatial gradient of a control field that impacts the qubit frequency. So if you've got a spin in a magnetic field, right? If you have a gradient of the magnetic field, the spin can lower its energy by moving in the magnetic field. And if you have the other spin state, it seeks the other field. This one wants high field as opposed to low field. So you can actually make a, cause the motion to be state dependent depending on how you apply this gradient. And actually, if you set up a superposition state of spins, you'll get a superposition state of motion. You can actually entangle the spin and the motion using these sorts of gradients. And if you have this gradient oscillate back and forth up and down at the motional frequency, then you can basically resonantly excite the motion in the same way that, if you're pushing a kid on a swing, at just the right frequency, you'll get them to swing bigger and bigger. And you can do this to excite motion in a state-dependent way. So one way you can do this is if you have a couple of laser beams and they cross each other and they have some interference fringe that moves at the difference frequency between the laser beams. And that basically makes a washboard that goes over the ions and makes this kind of a wiggly gradient. You can also have a magnetic field gradient that oscillates at the ion. But you can also do this without depending on the state. You can just use an electric field and couple to the charge of the ion and just wiggle the ion up by having an electric field resonant with the motional frequency. So how do we control these motional states, in sort of the actual what we put on for lasers and things like that frequencies? Well, we've got these two spin states a few gigahertz apart. We have an auxiliary state up here that's about a petahertz detuned. And then we can basically do our laser cooling and also prepare these spin states in an initial state using some weak resonant lasers. Then we use two detuned laser beams here to do this sort of spin motion coupling or spin flips. We can also use a microwave magnetic field or magnetic field gradient to do these sorts of things. And then if we want to excite the motion without caring about coupling to the spin, we can just use a resonant electric field at the motional frequency. And then we want to read out the motion. We read out the motion by coupling the motional state into this spin state and reading out the spin state. So if we basically turn on the lasers, we can choose the lasers in such a way that if you're in this spin up state, you're excited to an excited state here, and then you'll decay exactly back where you came from. And you'll keep cycling around many, many, many times. And each time you decay, you emit a photon in all directions. But if you're in the other spin state, there's no resonant level up here, and so you don't actually emit any photons. So what this looks like in the experiment is if you're in spin up, you'll see a little glowing dot if you look with a microscope objective and a camera. And this is actually just, you're seeing the fluorescence from a single ion here. And then you have to believe me that there's another ion here, but it's just not fluorescing. So we can't see any signal. But so we have this really high fidelity single shot way of knowing exactly what spin state the ion was in with this fluorescence. And then that, because we can map that with the motion, we can then determine what the motional state was. It's important to remember that this fluorescence involves letting lots of photons come out, and when these photons come out, the ion motion gets kicked. So now I'm going to shift gears and start talking about the electric field sensing that we can do with ion motion. So let's say you have an ion in a trap like this, and you turn on some sort of electric field, which is your signal to be sensed. And if that electric field is oscillating at the motional frequency, then the motion will increase. And this can be a coherent signal, or it could be noise that has some frequency component at the ion motion. But basically, what you find is if you plot the average motional excitation versus time, you will see it increase. And this depends on how much electric field you have. And I've actually got this wrong because I think it's E squared here. Anyway, and then so the idea is that the heating of this motion is a nice narrowband sensor for electric field. And again, we are sensitive to adding a single phonon of excitation, so we can sense really weak electric fields with this. I want to point out if you have more than one ion, you have these different normal modes and they have different sensitivities. So if you turn on a uniform electric field, you will excite the motion of this normal mode right here. But this normal mode will not be excited by a uniform electric field because it wants to push this ion and this ion the same direction, but that mode requires them to move opposite directions. And so in order to excite this motional mode here, you actually need a spatial gradient of the electric field. The electric field has to be different in magnitude at these two ions in order to excite this mode. So so this is sort of a feature that one can take advantage of in various ways. We'll talk about this later. But basically, we have a frequency and spatially selective electric field sensor. Now, I can't resist the temptation to embarrass our host slightly because she, for her PhD work, did some brilliant research on Heisenberg limited quantum enhanced electric field sensing with trapped ions, making really large superpositions of different number states of motion, and wrote this very nice paper here. So I encourage you to check that out. All right, now the fly in the ointment with this nice sensor is that there's motional heating that we don't want. That's not the signal that we want. We call this anomalous because it is higher than what we think it ought to be based on just sort of physics considerations. There's electric field noise that comes from the surfaces of our traps, and it basically kicks the harmonic oscillator. And the rate of this motion is a lot higher than you would estimate based on sort of the thermal noise from your trap electrodes. And it also gets worse and worse as you get the ion closer and closer to this electrode surface here. And that limits the ability to use smaller ion traps. So if we look at this, if we sort of take our heating rate, the rate at which we add motional quanta, if you want to do some kind of motional nanomechanics, you want a Q of, say, 10 to the 6, that means your heating rate needs to be sort of around here. And in principle, your noise floor ought to be below that. You ought to be able to make it. But this anomalous heating for a typical trap will sort of be something like this. So that means that it's hard to do small traps. You need to go to a pretty large trap where you're far from the surfaces to do really nice high Q stuff. Turns out that you can sputter clean the trap, or cool it cryogenically to reduce this. And I'll sort of talk about this here a little bit. So one thing you can ask is, well, does this anomalous heating effect depend on temperature? Does it depend on the material the trap is made of? Here's a very nice result from 10 years ago where the group at MIT Lincoln Lab showed that the heating rate goes down as you reduce the temperature, but it really doesn't seem to matter whether your trap is made of niobium or gold with the same design. Niobium has a really tough oxide and gold doesn't have an oxide, and yet they sort of show the same stuff. So the heating rate gets lower when you cool down, but it's basically material independent. But here's some later work from the Lincoln group as well, where they looked at traps, gold traps and niobium traps. And the red lines that we're seeing here are the same thing as fabricated. And we see it sort of looks pretty similar between these two as you cool down. The blue lines are after they did a sputter cleaning, basically an ion bombardment of the surface to remove contamination and oxides, and then remeasured the heating rate. And what you can see now is all of a sudden, these blue lines here look quite different between the two materials in terms of their shape and the absolute levels. And in fact, for this one, for the gold here, you can see sputter cleaning to remove contamination actually made the heating rate worse at lower temperature than it used to be before. So there is some material dependent behavior that one can find, once you sputter clean or go cryogenic, for example. But there's a ton of variables to test. And the problem is that most of the things you want to test, you've got to make and fabricate and install a new trap each time. So these data here were 5 traps that each had to be installed and operated and measured, and it can take a long time to cycle a trap around. This group developed a special method to be able to cycle traps rapidly just to be able to take these data. So this is really slow, and that's really challenging to be able to get to the bottom of what's going on. So what we've worked on in our group is what we call the stylus trap, to basically have rapidly interchangeable samples. And that will give us this sort of high throughput, tunable, repeatable measurement for surface noise. And so the idea here is that the trap electrodes look like this. They stick up from the surface of a chip, and the ion is sort of trapped above this center post. And if you look in the side view, it's sort of like this. So the ion is sort of up here, and the half space above it is open, and you can take a sample and bring it down close to this ion. And the closer it gets, the more the ion will see the electric field noise from this sample, and you can use it to characterize what's going on. Not only that, but you can take this sample after you've studied it with this ion as a probe, and actually move it in vacuum to other surface science tools or to places where you can do surface modification like sputter cleaning. And so this is sort of using this ion as a quantum sensor as part of a suite of surface characterization to try and understand what's going to make heating better, what's going to make it more viable for us to do ion trapping by understanding how do we make our surfaces cleaner. This is work that postdoc Kyle McKay and grad student Phil Kent have been sort of the leaders on. So here's some recent data of heating rate measurements with this trap that Phil has taken. So what we do is I'm plotting here the heating rate that we measure of the ion, and on the bottom, this is the distance of our sample to the ion. So when the sample is far away, the heating rate looks pretty flat, and we're dominated by the background from the stylus trap itself. But as we get in close enough, you see the heating rate start to rise. And this here is the signature of heating from the sample. And so now we're able to actually extract and determine, okay, this is the heating rate associated with this untreated gold surface that we have. We then took this sample. While still in vacuum, we transferred it to another chamber. We sputter cleaned it with argon ion bombardment. We brought it back and we measured it again. And now the heating rate looks like this. So now we're out here in the noise floor. But as we get in close, now here's this point, we can see we've reduced the heating rate. It's a lot closer to the background than it was before. And so this is sort of evidence that we've changed something about the surface to reduce the amount of electric field noise. And not only that, but before and after we sputtered it, we could take X-ray photoelectron spectroscopy on this sample. And here the red data show the spectrum before we treated the sample. You can see there's a strong peak for showing carbon and somewhat weaker peaks for gold. After the sputter treatment, the carbon peak is much reduced and the gold peaks are stronger. So basically there was something on the surface that was carbonaceous that went away. Now, this is not causative, we don't know, but this is some correlation. But this lets one think, okay, gee, we can maybe start to try to correlate what's going on in surface science probes with what we see from ion heating, and then efficiently with this rapid interchange get to the bottom of what's going on. So this is an exciting new direction for using trapped ions as surface science probes as quantum sensors. All right, next I'm going to talk about motional squeezing. So if you have a harmonic oscillator state, I can plot this in phase space here. And you see this sort of ground state wave packet here has sort of some uncertainty in both quadratures of motion. This is Heisenberg uncertainty sort of sets this. It turns out that we talk about squeezing. Squeezing is an operation that you can apply, and there's this squeezing parameter here that I will describe that basically trades uncertainty in one of these quadratures for uncertainty in the other. So basically, you can reduce the uncertainty in this quadrature in exchange for increased uncertainty in the other quadrature. This still obeys the Heisenberg uncertainty principle then, so we're okay. But it enables you to potentially be more sensitive. You reduce the noise in this quadrature if you're going to do some sensing there. So the way that we achieve this, and this is work that Sean Bird did for his PhD thesis, is we take our motional harmonic oscillator and we actually modulate the confining potential at twice the motional frequency. And so what this looks like in reality is that we apply some voltages to two of the electrodes of a trap, and ions live up here, and the modulation of the potential from these voltages squeezes the motional modes of these ions. So I won't want to go through the math in great detail, but basically if we have this parametric modulation, we apply it for a certain time, then we get squeezing. And the squeezing, we can control both the amount of squeezing with this time, and we control the phase angle of the squeezing with the phase angle of this drive modulation. So this is not a new idea. This is something that Dan Heinzen and Dave Wineland wrote a very nice paper about 34 years ago now. But we're able to do a really nice job in the lab now in studying this with some of the tools that we have. So let's say we make this squeeze state, right? How are we going to characterize whether we've made this state a squeeze state? Well, one way we can do this is to look at the motional state occupation in the number basis. So after we squeeze, we'll prepare spin down tensor with the squeeze ground state, and then we're going to drive that blue sideband interaction. Remember that blue sideband interaction is sort of a sigma plus a dagger type interaction for a varying duration. And what we get is something that looks like this. So we get a funky trace that these blue data, and then you can fit to it. And the red curve is actually a fit, and the fit is to a sum of sinusoids. And basically, we have good theoretical understanding that this sum of sinusoids corresponds to what the different Fock state populations are here. And from this, we're able to extract that our squeezing parameter is sort of about 2.2, which means about 20 dB of squeezing or thereabouts. And our populations and our Fock states are extracted and look like this. So this is characteristic of a squeezed vacuum state to see only even numbered number states are populated. There's other ways you can do this kind of a reconstruction too, but this is sort of an efficient one. Now, this tells you what the Fock state populations are, but it doesn't tell you anything about what the phase coherence is between them. So in order to understand the phase coherence, what we do is we squeeze and then we unsqueeze. And we can coherently squeeze and unsqueeze as unitary operations, and then just check, do we return to the ground state? And so basically, we're plotting here the probability that we return to the ground state as a function of the amount of squeezing. And so we can get, this is 20 dB basically of unitary, in other words, reversible squeezing that we can achieve using this technique. So this is some of the most squeezing that anybody has reported in any platform. So what can we do with these nice squeeze states? Well, we can use this squeezing. We prepare a squeeze state here, and then we can basically have a small oscillating electric field that does a coherent displacement of this motional mode here that we want to sense. So now, all right, we've displaced this by a small amount that is, could be resolved because it's smaller than the squeezed width. But unfortunately, the readout noise, the measurement noise itself, is this red circle here, is going to dominate the noise from the squeeze state, so we won't be able to read it out. What we can do, because this sort of detection signal-to-noise ratio, limiting the overall signal-to-noise ratio, what we can do is we can unsqueeze. And it turns out when you unsqueeze a state like this, you get a coherent state back. The coherent state is g times larger than this displacement that was to be sensed, where g is a gain that depends on the amount of squeezing that you did. And this is an idea that's been demonstrated in optics and known theoretically, and in in neutral atom spins has been known for a while. But basically the idea is we can get the SNR of the squeeze state, and we can preserve that in our detection here. And we get a gain that's basically exponential in the squeezing parameters. We should be able to get 20 dB of gain for this kind of quantum sensing. And it turns out that if we do this, we can get basically 17 dB of enhancement for sensing small oscillating electric fields above the standard quantum limit. So this is really nice, but the trick is it requires us to know the phase of this displacement with respect to the squeezing drive. So what if we don't know the phase of the displacement with respect to the squeezing drive? Well, this is work that was done. The theory was developed by Christian Ahrens, who is a professor at Arizona State right now, and he developed a method that he calls Hamiltonian amplification, which allows you to amplify the dynamics of Hamiltonians that involve the motion, even if you don't know this phase, the phase of some squeezing with respect to the dynamics that you want to do. So if you have a Hamiltonian that looks like some coupling between a motional degree of freedom with these A's and A daggers and some other system, this might be either an electric field or it might be a spin or something that's interacting with that motion. Then, and examples of this include both the sort of coherent displacements I was talking about, as well as like a Jaynes-Cummings type interaction. Then what you do is you basically do phase-sensitive amplification for one quadrature, just like we did, and then you alternate it. You change to the other quadrature and do that. And you basically do short bursts of phase-sensitive amplification in either direction, and you essentially trotterize the Hamiltonian that you want to amplify. And then overall, this gives you a phase-insensitive amplification of the dynamics that you want. Now, the gain here is not e to the r, but it's cosh r, which for large r squeezing parameter is basically e to the r over 2. And for those of you who are fans, as I am, of discussions of quantum limits of amplification, this is the factor of 2 that you have to trade if you go from a phase-sensitive amplification to phase-insensitive amplification. You have to add a half a photon of noise, or equivalently here, you get half the gain, so your SNR is degraded by a factor of 2. So we're again not violating quantum limits on noise here. So the way this works, again, is we squeeze, and then let's say we have a little displacement that we want to amplify. This displacement doesn't have to be along the squeezed axis anymore. It can be any axis we want. So I've sort of drawn an angle axis here. Then we unsqueeze, and when you unsqueeze, you amplify along this direction. You actually de-amplify along the vertical quadrature right here, but you end up with a coherent state kind of there. Then you squeeze in the other direction. You squeeze in the other direction here, and then you do the second half of this same displacement along the same direction, again comes out here. And then when you anti-squeeze the second time, you'll end up with you'll amplify in this direction, de-amplify in that direction, end up with a coherent state. But at the end of all of this, what you find is the relationship of this coherent state to the displacement is such that it's in the direction of this displacement, but you've actually made a coherent state that's larger than if you'd just taken the ground state and done the two displacements by itself. And the displacement is larger by this factor of cosh r. So you get this phase insensitive amplification. And so we demonstrated this with the motion of an ion. This is Sean Bird and Hannah Knock were the lead authors on this paper. And so what I'm plotting here is basically the gain that we see for amplifying a displacement versus the phase of that displacement. In other words, which direction did this point along the relative to the squeezing? So 0 would be if the displacement was along the anti-squeezing squeezed axis. And normally, if we'd done this phase-dependent squeezing I presented first, you'd actually would de-amplify your signal, so you'd lose. And that would be unfortunate if you were trying to do some quantum sensing protocol. So instead of having this strong gain but then potential for de-amplification, we can actually set it up where the gain should be uniform theoretically. That's this red line. And then the data that we show actually show that we have gain. We're above this gray line here. But it's mostly phase independent. So basically, regardless of what phase the displacement is at, we get gain no matter what. And the trade-off is somewhat lower maximum gain. And as you can see, we have a little bit of residual phase sensitivity. That's because of somewhat imperfect calibration of things in the experiment. But there's a lot of pulses that have to go in to get this to work. So anyway, so this was some nice work on quantum enhanced sensing with squeezing. Now I'm going to start talking a little bit about motional mode coupling and protected modes. So in quantum computing, there's a need for two ion species for cooling, and I'll explain this here. If you've got two ions here that are holding quantum information that you want to process, those are your qubits, your data ions. If they get hot, and you want to do quantum gates on them, you need their motion to actually be near the ground state in order to not get errors in your gates. So the fact that these ions have gotten hot from some kind of electric field noise, let's say, this is going to cause gate errors in your quantum algorithm. So you say, fine, why don't we just laser cool them? Okay, so you shine the laser on. The problem is that laser cooling changes the state of the qubits. So now you've basically erased and reset your qubits by laser cooling them. So this isn't something that you can just do. So what's the workaround? The workaround is to take these two data qubits and trap them in a well with a different kind of ion, which we call a helper ion. And the helper ion is chosen so that its laser wavelengths are different from the data ion's laser wavelengths. The data ions don't respond at the helper wavelength. So when everything gets hot, you laser cool the helper, and then everything cools down because remember the motional modes are sort of shared, right? So this is something that's going to be crucial if you want to do long algorithms in a trapped ion quantum computer. But if you look at these motional modes in detail, it's not quite as simple as the cartoon picture that I showed you. So here are the modes of, say, a two-ion mixed species crystal on these axial modes. And you can see that both ions participate in both modes. So if you cool the red ion, that's going to cool both of these modes. But in the radial direction, what you see is that there's some modes, like this one right here, where the coolant ion, the helper ion, has very little participation. So it's not going to be very efficient at cooling this mode down. And so that might be a problem for your quantum algorithm. It actually gets worse than that. If you have a three-ion crystal like this, there's three modes in this axial direction or in the radial direction. And this middle mode here, the stretch mode we call it, the helper ion does not participate at all. Only these outer two ions participate. So if you're just cooling this helper ion, you cannot cool this mode, this red mode here. It will not be cooled in any way. And so this is a problem. So because some of these modes are hard or impossible to do sympathetic cooling on, that's going to be a challenge for sort of quantum computing. So what can we do about that? Well, one thing we can do, and this is work that Panyu Ho pioneered as a postdoc, and Jenny Wu as well as a grad student who's finishing up her thesis now, along with a number of other folks who've been working on this and related topics in the lab here, is to actually couple modes together. So I'm showing here sort of a 3D view of one of these ion traps. This is more of this kind of 4-rod style of ion trap. And you've got ions in the middle here, and you've got all these electrodes around the side that we can apply voltages to. And what we're trying to do is modulate the confining potential parametrically. And so we're going to take that confining potential with this 3-ion crystal, and we're going to add this cubic term, for example, and we'll have this oscillate up and down. And that is going to couple this alternating mode to this stretch mode right here, right? So, so this is going to enable us to actually exchange motional states between these two modes that are coupled, and that's going to let us cool this mode indirectly. So, and I want to point out that there's been, understanding of these sorts of things for a long time, and various other work that has been done both at Berkeley and Lincoln Labs in Oregon, in addition to the work from our group around this topic. So let's say you've got two modes, and here's how you're going to indirectly cool them. So let's say you've got a weakly cooled mode right here and a strongly cooled mode right here, and they're both in some thermal state. They're not in their ground state. They have occupation in these higher states. So you're going to start out by cooling, and you're going to cool the strongly cooled mode. You're going to get it down to its ground state, right? And then what you're going to do is you're actually going to do this motional coupling. You're going to swap the motional modes. So now you basically swap this ground state population into the weakly cooled mode, and then you have the strongly cooled mode is hot again. And then you cool the strongly cooled mode again, and now both of these modes are cold. And you've done it through this sort of indirect cooling via swapping with this parametric modulation. And so what we're able to do here is we're able to show after different rounds, 1, 2, 3 rounds of this kind of cooling, swap, cooling, we can take modes that initially had one or a few quanta, and we can cool them down so that even this impossible to cool mode, which is here in the pink, the stretch mode that has no participation, has 0.02 quanta of motion in it. It's basically it's in the ground state. So this is a really nice way to be able to cool these and access these nominally not coolable modes. Furthermore, this mode coupling is a quantum coherent process. So we're actually applying a Hamiltonian that looks like this, where there's some coupling strength that we control, this G. There's a phase of the coupling, phi, that again, we get to control. And then we're coupling these two modes with this sort of beam splitter type, swap type interaction here. And so we can do things like start out with 1 quantum in one mode and 0 quanta in the other mode, and turn the coupling on and sweep the frequency. And as we sweep the frequency of the parametric modulation, we see that when we're resonant with the frequency difference between the modes, we swap population out of the alternating mode and into this stretch mode. So the alternating mode population goes to 0, the stretch mode population goes to 1. If we're off resonant, we don't do this swap. We can sit on resonance here and then basically just drive this coupling, and we can see the quanta swap back and forth. We could do a beam splitter interaction. We can do a full swap. We can do a double swap when you get phase shifts associated with these things. So all of this is sort of quantum coherent operations. Another thing that you can do that's pretty cool is you can actually do Hongo-Mandel interference, not with photons as in the original Hongo-Mandel experiment, but with phonons. And not only that, but phonons at different frequencies. So here's a phonon in the alternating mode and one in the stretch mode. These phonons have different energies, different frequencies, because the modes have different frequencies. We couple them together, and you see we start off with population in this 1-1 state here, and then after some time we swap so that there's no population in the 1-1, but instead we have 0-2 plus 2-0. And this is basically this constructive interference that these phonons, because they're bosons, want to basically both be in one mode or both be in the other mode when you couple them together. And we can have this oscillate back and forth. I want to point out beautiful work from the group in Osaka who did this with same frequency phonons a number of years ago. This is now using different frequency phonons and sort of a controllable coupling that can be turned on and off in ways with phase control here. And so we can use all of these tools. We can actually create a Bell state between these two modes, an entangled state between the two modes. The lower bound of the fidelity is here. Unfortunately, we didn't take the data we wanted to really nail down the fidelity, but this is a pretty good fidelity. And then you can swap the population, and the error when you swap the population back and forth is about 1.5%, and that's dominated just by motional heating from background noise. So it could be better in a different trap. So not only does this give us the ability to do these sort of quantum coherent swaps and things, but it lets us do something new, which is to protect motional states. And I'm going to explain what this means. So here we are. Here's our crystal. Here's this stretch mode. This stretch mode, again, has 0 participation from our magnesium ion, our helper ion here. So we cannot cool it with magnesium. But another way you could look at this is that you're protected from any photon recoil that happens on that magnesium. So if the magnesium is fluorescing, that also won't kick this stretch mode of motion, although it will kick these other modes of motion. So the idea is if you have a motional state of interest, some quantum state that you want to store, you can store it in this stretch mode during when you do a fluorescence readout of magnesium. And if you do that, then you won't impact, you won't destroy the motional state that you've stored. So if you have a motional state that might be, for example, a quantum error correcting code or some interesting cat state or something, and you want to learn about it, you can map information about that mode onto the magnesium spin and then swap the mode into the stretch mode, swap the state into the stretch mode, read out the magnesium spin, and now you've learned the information about the mode, but without destroying it. So you can do repeated measurements now. This is something that hasn't ever been able to be done before with ion motion because of this problem of photon recoil destroying modes. And so really this sort of opens the door to being able to do quantum error correction on motional states as sort of continuous variable quantum computing applications in ions, for example. And so we tested this out. We did an experiment. We set up this nice motional superposition state, and then we swap it into the stretch mode, and then we read out the magnesium ion. Now, this is a very sensitive state here, this superposition. If you scatter photons and cause recoils, then this state is going to decohere. And if you try and do an interferometric Ramsey measurement at the end here, you're going to lose your contrast. But what we found is that basically the Ramsey contrast, and the error bars are somewhat larger, but the Ramsey contrast basically doesn't change, basically stays all the way high, even after we've scattered several thousand photons from this magnesium ion. We've detected many, many photons. So, and we only detect a couple percent of the photons that are actually scattered. So we're actually doing a really good job of protecting this mode. And so we want to work more with this technique in the future. So in the last minute or two, I just want to touch on some coupling that we can do with motion in different wells. This is work that grad student Justin Niedermeyer is finishing up for his PhD thesis, and postdoc Nathan Lisney, who's now has moved on to his next job, is also done a lot of work on. And now, along with a number of people, including again our host Katie McCormick, laid a lot of groundwork for this experiment. So we've got a trap here that is a tunable microtrap array. We call this a triangle trap because here's sort of a 3D projection of the electrodes. And we've got this sort of funky pattern of electrodes. We put RF on the blue one, and this makes 3 separate potential wells. So now these ions are not sharing a well. Each one has its own potential well, and each potential well can be individually tuned. And these wells sit 30 microns apart up in this sort of hovering above this surface here. So the idea is we've got a well here, we've got a well there, 30 microns apart. Let's put an ion in each one. If the wells have different motional frequencies, like this one's a little bit softer than that one, then not much interesting happens. But if you bring the well frequencies on resonance, now you'll actually get a coupling between the motional modes of these 2 wells. And this is basically, you've made coupled harmonic oscillators here, resonantly coupled. And the strength of this coupling depends on this distance between the wells, on the confining potential frequency. We've worked hard to get this distance as small as we can, the ions as light as we can, et cetera. So we get sort of a 3 to 4 kilohertz coupling between these wells. And so then if you actually have 2 ions that you couple like this, let's say we take 2 ions here, and we use voltages on these electrodes to tune their motional frequency in and out of resonance. Spectroscopically, you see something like this. You actually see an avoided crossing, where as you tune the 2 motional mode frequencies through each other, the fact that they're coupled to each other lifts the degeneracy, and now you get an avoided crossing here. So this is exactly the same kind of thing as you would see, for example, in a vacuum Rabi splitting as you tune a qubit through a resonator, let's say. But this is just two harmonic oscillators that are coupled to each other. So this sort of stuff has been demonstrated before in trapped ions, but so here we're doing it in this sort of triangle setup. So here we are, and this splitting we expect to be twice the coupling, and in fact that's where it is. And our simulations of what the mode frequency should be doing agree pretty well with our data. So what happens then if we put these two motional frequencies on resonance and we inject a single phonon, just one phonon, and then let's just measure over time the probability of the phonon being in, say, the left well of these two wells. We get oscillations like this. So this is basically the phonon swapping to that other well and back and forth and back and forth. This is 100 swaps. This is 200 swaps. This is a single phonon that's swapping coherently hundreds of times between basically the motion of one ion and another ion that are 30 microns apart. And we can zoom in on some of these zones here, and you can see there really is sort of nice coherent flopping back and forth. And the rate at which this flopping is occurring agrees again with our calculations for what the coupling strength should be between these wells. So we're seeing hundreds of coherent swaps of a single phonon. So this is I think more phonon swaps than anybody has seen before. So this shows we've got some pretty nice harmonic oscillator control here. So all right, that's two wells, but we've got a triangle trap, right? So let's make a triangle. So what do the motional modes look like if you have a triangle? So actually, if you tune everything on resonance, you've got three types of eigenmodes here. One is this sort of breathing-y type mode. One is this sort of two go out and one go in mode. And then the third one is this one goes in, one goes out, and one does nothing. And actually, you know, the symmetries of this are such that there's some degeneracy around which ion is the one that's the in or the not coupled here. And so there's it will be not defined which orientation this has. So if we look at this, these two modes here will involve all three ions. This one only involves two of the ions. So if we look at the spectrum here, we get something that looks like this. So we get this avoided crossing that we can see right here. And then we get this other line as we're tuning the mode frequencies. And this line just tunes right through. So why does this tune right through? That's because these on resonance here, which is where I'm plotting these eigenmodes, on resonance, this mode here doesn't actually couple to this mode or that mode. If you do the dot product site by site, the dot product of the top is 0, the dot product of these things has the opposite sign of the dot product of those things. Those modes don't couple to each other. And same thing with modes 1 and 2. And so this mode here just tunes through while these other modes here couple to each other. And so we see this sort of spectrum here, and then we can tune to different areas. The eigenmodes look different as you tune away from resonance here. We can tune to these different areas and say, what happens if we put a phonon in and let it swap around? So here we are. This is a single phonon, which is basically being delocalized over three ions that are each 30 microns apart in a trap. And this phonon is coherently wandering around between all these sites, and it's doing so in this way where we see these beating frequencies that tells us that multiple types of exchange are happening. If we fit to these frequencies here, we can actually extract, all right, there's three frequencies going on here, and these are those frequencies. If we tune to a different set of motional frequencies, now the phonon population oscillations look like this. If we tune to yet another one, now they look like this. And again, we've got more than one frequency here. And we can actually fill this in. And what we can see is that all of the measured frequencies, the beats of these phonons coupling around between these three modes agree with our simulated prediction of what we should have as we're coupling between modes. So this is a really nice way of showing that we have single phonons that we can control and get these to coherently delocalize and refocus over these wells that are spaced 30 microns apart from each other. So it's kind of a cool non-local phonon. So with that, that's the last of the results that I want to share with you. And I just want to thank you all for tuning in and listening. There are many people who have worked on all the things that I've discussed in this talk here. I've listed their names here: Dave Wineland and Andrew Wilson, and then particularly Didi Leibfried is sort of my co-PI on all of these things as well, but this is sort of the PI crew. We've also had trap fabrication help from other folks, and then fidelity analysis folks. And then again, if people are interested in PhD or postdoc positions, you can give us a call. Here's our website, here's our group. And thanks for your attention. I'm happy to take questions that have come in.
All right, thanks, Daniel. That was really exciting to see the triangle trap working so well.
Yeah, that's great.
So we have one question. Somebody asked why 30 micron? I think they're talking about the spacing between the ions in the triangle trap.
Yeah, well, so that's a good question. And basically, the answer is because it's really hard to get 3 separate potential wells any closer than 30 microns and have them still be individually tunable. So you can see the ions live some distance above the surface here. And so if you want to make them closer to each other, you actually, in order to do that, you kind of have to bring them a little bit closer to the surface and make these electrodes smaller as well to have that work out. And so we're kind of running into limits of how small these can be microfabricated. There's vias under these and things like that. And these are sort of, you know, on the order of 10 micron electrodes with a couple micron gaps in between them or something like that. So it becomes challenging to get a trap like this to yield properly and not have, say, electric breakdown. Also, if you have laser beams coming in, they have to skim over the surface. You need enough clearance under the ions for the laser beams to go without just scraping on the trap, and that will wreak havoc on a lot of things. So that's sort of the practical limitation that sets us to 30 microns.
Cool. And then I had a question about the previous section where you were talking about the sympathetic cooling and the protecting the motional state. So I was curious how like heating comes into play here. Is that you were talking about how the motional state is protected by fluorescence from the helper ion, but is there a way to like kind of hide the useful motional states in some mode that is less sensitive to heating, or is that not really a practical way of doing it?
No, that's you absolutely can. And so you know, if you think back to I tried to show this at the beginning, but if you have all the ions sort of moving in the same direction, that mode will be sensitive to sort of you know, uniform electric fields. And so those tend to heat faster. If you have a mode like this stretch mode, this will also be insensitive to heating from uniform electric fields. This only will heat if you have a spatial gradient of the electric field. And so as a result, I mean, we see this in the experiment that we've done this on, that the in-phase mode heating is a lot higher than the stretch mode heating. And so even if you just take a motional mode and swap it into the stretch mode, you benefit from the lower heating in that mode, even if you're not doing fluorescence readout as well. The trap that we did these experiments in, unfortunately, has a higher heating rate than would be ideal for these things. And so we will plan to go to a new trap in the future, and the heating rate should be a lot lower, hopefully there, and that should let us do more things. But yeah, absolutely. You know, when you have many ions in a crystal and you have sort of high order modes like that, those are increasingly insensitive to electric field noise and have increasingly low heating rates. So those are great candidates for storing motion coherently apart from heating. Now, you still have to worry about motional dephasing, which is another form of decoherence I didn't really touch on. But if the confining potential changes over time, then that basically changes the energy of the motional mode, the frequency of the motional mode, and you'll get dephasing in the same way that if you have a qubit whose frequency is changing in time, that will dephase the qubit. So that means that you have to have really steady potentials applied in order to keep the motional modes having really steady frequencies that don't drift in time.
Right. Okay. Okay, I think that was all the questions. Well, thank you very much for a fantastic talk, Daniel. And of course, a big thanks to everyone for tuning in. If you liked this video, go ahead and show us by clicking that button. And if you want more of these types of videos, definitely make sure you're subscribed to the channel. If you want to continue the conversation, hop over to the Qiskit Slack workspace. We'll be off next week, so we'll see you again in 2 weeks.
Great. Thanks, Katie. Thanks, everyone, for listening. This was lots of fun to share.
Bye, everyone.
Bye.